This is the part 2 of chapter 4, non-faradaic processes. In the subchapter 1 and subchapter 2 about the electric double layers, you have got the concept and also modern model of the electric double layers, followed by how to measure the capacitance value. The method was based on the electrocapillary effect. In this subchapter 3, I'd like to give you a history of models for the electric double layers. The first model was given by Helmholtz at 1879, which is based on a single charged layer. Here we have an electrode and electrolyte. The electrode is electrified by 4 excess negative charges. And what happens on the side of the solution? To compensate the excess charges, then we could use the 4 cations on the side of electrode. Then those 4 cations are compensating the 4 negative charges developed inside of the electrode. That was the very simple idea presented by the Helmholtz at 1879. That is to say, Helmholtz model is a physical model in which a single layer of ions is absorbed at the surface like that. Excess charge developed in electrode here are compensated only by a single layer. I'd like to emphasize a single layer. Actually, you have already known that the modern model of electric double layer. In that model, we have a solvent layer between the electrode surface and the outer Helmholtz plane. However, in the very first model given by Helmholtz, there is no solvent layer between the electrode surface and the outer Helmholtz plane. Only thing we have in this model is just cations or anions to compensate the excess charges of electrode. It is a very simple model. It was the first starting for the electric double layer sketch. In this model, potential independent capacitance was assumed. So, capacitance of double layer by Helmholtz is not the function of potential. So, capacitance is independent of potential like that, constant, with respect to potential. This capacitance can be described by this equation. Here you can find some distance from the electrode surface to a position. So xh means actually the distance between two plates for the capacitance. So one capacitance considered as the electrode, the other capacitance, the other plate as the outer Helmholtz plane here. And epsilon indicates permittivity, so epsilon r is relative permittivity of electrolyte, and epsilon 0 indicates the permittivity of vacuum. So the epsilon 0 is a kind of constant, or however, epsilon r is the property of electrolyte. So, I mean, the capacitance value is inversely proportional to the distance between two plates, or the thickness of Helmholtz layer. Then, let me get this equation into the basic equation about the capacitance definition. As you know, the capacitance can be defined by the Coulomb, or the amount of charges per potential. So potential is equal to some charge per capacitance. And then therefore the potential is inversely proportional to the capacitance. Also at the same time, the capacitance is inversely proportional to the thickness of Helmholtz layer, or the distance between two plates. Therefore, the potential is just proportional to the Helmholtz thickness, or the distance from the electrode surface. So here is the potential profile, which is expected from the Helmholtz model. X-axis, the distance from the surface toward the bulk electrolyte, and y-axis is the potential. The upward direction is assumed to be minus here. Then at x equal to 0, of course, we have the potential of metal plate. This potential of metal plate could be determined by your applied potential. And then that potential is compensated by the cations in this case. So it is going down linearly, because based on this equation, and then finally reach the potential of the solution or electrolyte. So for this Helmholtz model, we have this kind of linear decrease or linear increase potential profile for the electrified electrode. However, okay, so anyway, I have said Helmholtz assumed that potential independent capacitance. However, this assumption is not true, as you know. In the subchapter 2 for the electrocapillary effect, you have learned that the capacitance would be minimized at point of zero charge. As the potential moved from the point of zero charge toward the positive direction or negative directions, the capacitance increases. However, in this assumption, in this model, we have assumed the capacitance is not depending on the potential. So it's not true. Therefore, the Helmholtz model should be modified or replaced by a new model. Then let's go to the second model. The second model is presented by Gouy and Chapman around between 1910 to 1913. So they developed the diffuse layer. You have learned about that already in the modern structure of electric double layer. To satisfy experimental evidences of the potential dependent capacitance, like that, right? You have seen these pictures from the previous subchapter 2. Gouy and Chapman developed a model for diffuse layer independently to each other. In the Gouy-Chapman model, excess charges developed in an electrode are compensated by charge distributed multiple layers, like that. You know, in the Helmholtz model, we have assumed just a single layer that can be responsible for compensating all of the excess charge of electrode. However, in this Gouy-Chapman model, we need to have multiple layers. Like first layer, cation is dominant because your electrode is electrified negatively. The second layer, the smaller number of cations. The third layer, smaller number of cations. I mean, the cations are distributed through the volume of the electrolyte to compensate the electrified electrode. And also in the GC model, Gouy-Chapman model, potential dependent capacitance was assumed, like that. So let me take a look at the Gouy-Chapman model in advance. Here is the potential profile. X-axis, as you know, the distance from the electrode surface toward the bulk electrolyte. Y, the potential. So the starting point is, of course, the potential of metal plate. So here, and then this negative potential is compensated by cations in the electrolyte through the multiple layers of electrolyte. So the potential is going to the direction of positive values. Then it is going down. Finally, at the end of the double layer, diffuse layer thickness, then we could reach the value of the potential of solution or electrolyte. Let me decrease the concentration from C1 to C2. Let me say this is the 10 millimolarity. However, C2 is like 2 millimolarity. Then what happens? What kind of things can you expect? At a lower concentration of ions, I mean I'm changing the concentration from C1 higher to C2 lower. The excess charge of electrode is compensated by counter ions, in this case cations, within a thicker diffuse layer. I mean the XDL, or diffuse layer thickness, is thicker and thicker as your concentration of ions decreases. As you know, because we have smaller number of ions in the lower concentration, it means to compensate the same amount of excess charge developed in electrolyte, we need to have thicker volume of electrolyte. So when we are going from the higher concentration to the lower concentration, we need to have a thicker volume of electrolyte. That is to say, the diffuse layer thickness increases with decreasing concentration. Let me derive the equation for the Gouy-Chapman model about diffuse layer. Here is the situation. I have an electrode, and here is the electrolyte. X-axis comes from the surface of electrode to the bulk electrolyte. Right now, I'm applying a negative potential into the electrode. Therefore, to compensate the negative charges developed in electrode, then cations are accumulated around the surface and then going down. So here N sub I indicates numerical concentration of ions, species I. So in this case, let me say sodium plus ions. The numerical concentration would be maximized at the surface to compensate the excess charge of the electrode and then going down. At the bulk, we would have some bulk concentration. Let me say it is the N sub I with superscript 0. Along the x-axis coming from the surface to bulk electrolyte, we have another axis for the potential. Here is the new definition about the potential. Here phi delta. Phi delta is equal to some potential phi minus solution potential here. So at x equal to infinity, or in the bulk electrolyte, phi delta is 0 because the potential of bulk is phi of solution. At the surface, the phi delta would be your applied potential minus phi of solution. So let me define it as phi delta 0. 0 indicates the surface. With this picture and parameters, let me start with the Boltzmann equation to describe charge distribution. So following the green line, the numerical concentration of, for example, sodium plus is equal to the maximum value is Ni0. This concentration is the value you have introduced into the electrolyte, like 1 molarity of sodium chloride or something like that. Then exponential minus Gi. Gi indicates the charge, number of charge of species I. E means point charge of electron, and phi delta potential per Boltzmann constant with temperature. Then rho x, rho as a function of x is charge density, is equal to the summation of all species of product of numerical concentration of species I with the corresponding charge, number of charge, and point charge. So Ni comes from the Boltzmann equation, so charge density can be described by Boltzmann equation with some summation. Then let's go to Poisson equation. Actually, I'd like to obtain the potential profile around the surface. I mean phi delta as a function of x. So to obtain the phi delta profile, we need to have Poisson equation. The second derivative of phi delta, or potential, with respect to the distance from the surface of electrode, is equal to minus charge density per the permittivity, relative permittivity with the permittivity of vacuum. This and the charge density comes from the previous equation, and then we could obtain the Poisson-Boltzmann equation. I mean, after combining the Poisson equation with the Boltzmann equation, we could obtain the governing equation, which is the Poisson-Boltzmann equation. The second derivative of potential with respect to the distance comes from the Poisson equation, and on the right side you can find the Boltzmann equation. Then the second derivative could be described by 1 over 2 the first derivative of the square of the first derivative. So after taking the integration for both sides of equation, then the square of the first derivative is equal to the integral of this equation. That is the governing equation, or Poisson-Boltzmann equation is governing equation, and then here is the boundary condition. From the picture, we could obtain some boundary condition. At x equal to 0 on the surface, then the potential is phi delta 0, or your applied potential minus solution potential. At x is going to infinity, or when you are going to the bulk electrolyte, then phi delta should be 0 because its potential is solution potential. Or the first derivative of phi delta is going to 0 because the potential is saturated or converged to the phi delta here. Okay, so right now we have governing equation and boundary equations. Then we could obtain the phi delta as a function of x. Still, we have governing equation, boundary condition, which comes from the previous slide, and this is OD. So we'll obtain the potential profile around the surface. After integration, you have this equation from governing equation to this one with boundary condition. Then here is the square. So by taking the root square for both sides of equation, then the first derivative of potential or phi delta is equal to this equation. And you can recognize that the first derivative of potential is the hyperbolic sine function of the potential. The definition of hyperbolic sine function is like that: e to the x minus e to the minus x per 2. So it looks like this one. Then right now we have a first derivative, so by taking the integral for both sides of equation, then here, then finally it is going to the final equation like that. You can find the hyperbolic tangent function of potential, and by reshuffling this equation and also by getting together some parameters into one parameter, then you have obtained this one: hyperbolic tangent function of GE phi delta, that is the potential for KT, and in the denominator the value of the potential at the surface is there, so this is some value, is equal to exponential of minus x, the distance, per some value. It is called XDL, or thickness of diffuse layer. XDL can be described by several parameters and constants. So let me check some parameters. Relative permittivity, which is the property of your electrolyte. Constant, just temperature and constant. And numerical concentration of species I at the bulk electrolyte is also the extensive properties of species I. And G, charge, number of charge for the species I, and the other thing is constant. So diffusion layer thickness is determined only by electrolyte properties, those three things. There are no information about the electrode is involved for this equation. So everything is determined by the properties of electrolyte. The one of them, which is the concentration term, I mean the bulk concentration term, the diffuse layer XDL is inversely proportional to the root square of the concentration of species I. At room temperature, and if you have 1 molarity of ions in water, then XDL value is going to about 3 Armstrong, or 0.3 nanometer for 1 molarity. If you are using a more dilute solution like 100 millimolarity or 10 millimolarity, then of course the diffuse length, I mean the thickness of diffuse layer XDL would increase with the decreasing concentration. So maybe several nanometer or 10 nanometer or something like that as your concentration decreases. So right now we have here we have the first derivative of potential function, which is the hyperbolic sign of the phi delta. And let me think about that. Let me think about the situation at x equal to 0, or let me focus on the surface of this situation. So at x equal to 0, the first derivative of potential here and the product of this value with the permittivity, that you could obtain the excess charge density. So it is follows hyperbolic sign still there, and then the first derivative of the excess charge of metal plate with respect to the potential is going to finally capacitance. C capacitance, D for diffuse layer, and GC is Gouy-Chapman model. And then after the first derivative, this hyperbolic sign is going to hyperbolic cosine, and hyperbolic cosine looks like this one. So finally we could obtain the capacitance function, I mean capacitance function of potential. So at point of zero charge, you would have a minimized value. However, far from the point of zero charge, the capacitance value would increase like that. So this is the Gouy-Chapman model equation about the concentration. Again, let me check again. Capacitance of diffuse layer by Gouy-Chapman is equal to some value with root square of concentration and hyperbolic cosine of potential. Again, capacitance is proportional to the root square of concentration and the hyperbolic cosine function of the potential. That is the Gouy-Chapman model. And finally, we could describe the potential dependency of capacitance, which is very different from the Helmholtz model of electric double layer. Here is the third model of electric double layer proposed by Stern at 1924. In this model, the Helmholtz layer and also Gouy-Chapman model is combined to each other. Right now we have Gouy-Chapman model. The Gouy-Chapman model solved the problem of potential independency of Helmholtz model. So right now, the capacitance expected by the Gouy-Chapman model is potential dependent. So at point of zero charge, the minimum value of capacitance is obtained. Far from the point of zero charge, the capacitance would increase with the potential. But there is a problem in Gouy-Chapman model still there. Let me check up the value of the capacitance expected by Gouy-Chapman. Here I have sodium plus and chloride minus in water, or copper 2 plus and SO4 2 minus in water. That is to say, this kind of salt is named by G plus to G minus salt. It means we have the same number of charges for both anions and cations. So sodium plus, chloride minus, each ions has the 1 plus and 1 minus, or in copper sulfate has 2 plus and 2 minus for its own number of charges. So we are thinking about this kind of G plus to G minus salt. And water has the relative permittivity, or dielectric constant, is equal to 78. And let me assume that our electric double layer is formed at 25 Celsius degree. Then we could calculate some value about some parameters of Gouy-Chapman model, and finally we have obtained the capacitance value for diffuse layer expected by Gouy-Chapman is equal to 2 to 8, the number of charge, and the bulk concentration, the root square of bulk concentration, with hyperbolic cosine of 19.5 Z, the potential microfarad per centimeter square. If Z value is going to 1, I mean plus 1 or minus 1, and if you are using 1 molarity concentration and at 1 volt, then the capacitance value is going to 228 microfarad per centimeter square, this value. This is the problem, because experimentally the capacitance of double layer is measured between 10 and 30 microfarad per centimeter square centimeter. It means the capacitance value estimated by Gouy-Chapman is overestimated when compared with the experimental values, or the value is too deviated from the real value. So how can we modify or fix this problem? Stern proposed a solution, inserting Helmholtz layer. In Gouy-Chapman model, we don't have Helmholtz layer, only diffuse layer, and nearby on the electrode surface. But Stern have tried to insert the Helmholtz layer between diffuse layer and electrode. So right now we have Helmholtz capacitor and Gouy-Chapman capacitor, both of them in series. Then let me check the overall capacitance value based on those two capacitances in series. 1 over the capacitance of the overall capacitance of double layer is equal to 1 over Helmholtz capacitance plus 1 over Gouy-Chapman capacitance based on reciprocal summation. Then the Helmholtz capacitance can be described by the permittivity to the thickness of Helmholtz layer, like 3 Armstrong or something like that, plus 1 over here the equation for the Gouy-Chapman model. By using these equations, the values of electric double layer capacitance is going to the range between 10 and 30 microfarad centimeter square. Here is the graph of capacitance versus potential. And I have two curves here. The blue line for the Gouy-Chapman model, and the dashed red line is for the Helmholtz line. So let me think about the potential around the point of zero charge. Of course, you would have the minimized value of capacitance for the Gouy-Chapman curve around here. At this potential, Helmholtz capacitance value is estimated to be much larger than the capacitance expected by Gouy-Chapman model, like that. It means 1 over CH Helmholtz is going to the smaller number, and 1 over Gouy-Chapman model is going to the larger number. So the overall capacitance could be dominated by the Gouy-Chapman model. So it means the capacitance value of the double layer is approximated by the capacitance expected from the Gouy-Chapman model. So for the overall curves around the point of zero charge, you could have this blue line. Around the point of zero charge, that is to say, capacitance shows potential dependence following hyperbolic cosine of potential. And let's go to the potential here and there far from the point of zero charge. So we will focus on this region and this region. In that case, the Gouy-Chapman is much larger than the Helmholtz. So this value 1 over Gouy-Chapman is going to the smaller value, and the 1 over Helmholtz is going to the larger value. So the overall capacitance of double layer is approximated by Helmholtz capacitance. So let's go back to the curve, and at this region you have the Helmholtz instead of Gouy-Chapman. In this region, far from the point of zero charge, capacitance is potential independent. Electrode attracts ions to its surface strongly, so all the potential drop is restricted only within the first compact layer. Therefore, the diffuser layer cannot affect the capacitance. The overall capacitance curve follows like that. So saturated one, and then going down finally reach to the minimum value of capacitance and going back up to the higher value and then saturated. So this is the standard model consisting of Helmholtz plus Gouy-Chapman in series. Grabbing the standard model, let's go to the 1947. Grahame has added one more things into the standard model. That is the specific adsorption. So right now we have diffuser layer. Also, just on the surface of electrode we have a Helmholtz layer. Actually, we didn't have the solvent molecule layers yet. Grahame have added the specific adsorption layer onto the Helmholtz layer. That is the Grahame model. For example, chloride anion is a representative species as the specifically adsorbed ions. The strength of specific adsorption is in the level of chemisorption or covalent bonding. Therefore, the interaction between the chloride minus ion and a negatively charged electrode is strong enough to overcome the electrostatic repulsion. So you could find specifically adsorbed anions on the surface of electrode, even you have applied a negative potential. Of course, when you have applied a positive potential. That is the standard model. And let me try to take a look at the potential profile here. And y-axis is the potential, the upward direction is going to the more positive value here, and x-axis is the distance from the surface of electrode toward the bulk electrolyte. Here is the inner Helmholtz plane, where you can observe the chloride minus anions specifically observed on the surface of electrode. And here is the outer Helmholtz plane. That is the plane to having the counter ions to compensate the excess charges of electrode. In any cases, okay, so let me explain about that. So let me think about the 0.3 molarity sodium chloride on mercury at 25 Celsius degree. We could expect that chloride minus anion is specifically observed on the surface on the mercury electrode. I'd like to apply several potentials into the electrode. In any cases, the potential goes from the applied potential on the electrode, EF on the surface, to the electrolyte potential in the bulk electrolyte, or potential of solution. Here, ES is solution. The specifically adsorbed anions alter the potential profiles significantly, particularly when a potential more positive to point of zero charge is applied. So let me explain about that in a more detailed way. Here is the starting point, which is the point of zero charge. I mean, you have applied a potential which is equal to the point of zero charge. In this case, EF, or applied potential, should be equal to the potential of inner Helmholtz plane, including chloride minus anion. That is the definition of PGC. At point of zero charge, no excess charge on the electrode and no excess charge on the electrolyte around the interface. So it should be the same. Around zero, actually. Okay, then of course the potential goes up to reach the potential of solution. That is the situation at point of zero charge. Then I'd like to decrease the potential, our applied potential, into the more negative value. So the potential value of EF is more negative than the point of zero charge. So the starting point would be here at a more negative value. And due to the repulsive force, in this case, 10% of electrode surface is covered by chloride minus. Okay, I forgot one more thing. So let me assume that 30% of electrode surface is covered by chloride minus anions in the case of point of zero charge. That is the starting point for comparison. However, when you decrease the potential into the more negative value, the percentage is going down. Like schematically, let me say 10% of electrode surface is covered by chloride minus anion. That is to say, the effect of chloride minus on the potential profile becomes less. Any significant indication of the anionic adsorption is not observed in this potential profile for the EF more negative than PGC, point of zero charge. Let me read this curve again. The potential increases monotonically, right, from the negative EF a long distance by the charge compensation by sodium plus. Finally, the potential is recovered to the E of solution, the potential of solution, while electrolyte, in the bulk electrolyte region. So it's not very characteristic behavior. And finally, let's go to the EF, which is more positive than the point of zero charge, so positive potential. Due to the attractive force of the between the positively electrified electrode and the chloride minus, 50% of electrode surface is covered by anions. This is the highest value of coverage by chloride minus ions when compared with the point of zero charge case, that is 30%, and the negative potential case, which was the 10%, right? So we have a lot of chloride minus anions on the surface of electrode due to the specific adsorption. It happens because we have a more population of chloride minus anions around the surface of electrode because we have applied a positive potential. Therefore, the effect of chloride minus on the potential profile becomes amplified. Then the potential drops abruptly from EF to the potential at inner Helmholtz plane of chloride minus anions. Then potential goes up again to reach the solution potential. Therefore, the characteristic potential minimum point here of specific adsorption is observed. Then you could distinguish this situation from others like PGC or negative potential less than PGC. Then this kind of potential profile, if you can obtain it, is the characteristics of the specific adsorption. Still, we are on the Grahame model about specific adsorption. So how did he propose this kind of specific adsorption to the model of electric double layer? Let me start with the Gouy-Chapman model. Around 0, even in the Stern model, your capacitance or surface tension behavior follows the Gouy-Chapman model. Then let me think about the Gouy-Chapman around the PGC. Gouy-Chapman model doesn't have any parameters related to the identity of ionic species. Let me check the equation for the Gouy-Chapman here. And epsilon, that is the permittivity of the solvent molecules. And the other thing is constant. Here is the concentration of ionic species, but it is not related to the identity of ionic species. It is just the amount. The other thing is potential. That is the parameter you have fixed. And how about G? Right. G is related to the identity of ionic species, like +1, -1, +2, -2, or something like that. However, if you compare between the electrolytes having the same value of Z, I mean number of charges, like sodium plus and lithium plus, then it is not important parameters to distinguish between ionic species. So even in that case, I mean the Gouy-Chapman model cannot distinguish between ionic species if they have the same number of charge. So even in this case, however, different electrocapillary curves were obtained from different ions at the same concentration. Look at that. Let me take two curves. This is sodium chloride and this is sodium plus. The value of Z, I mean the number of charge, are the same, +1, +1, -1, -1. And it means Gouy-Chapman model cannot distinguish between sodium chloride and sodium bromide because they are in the same solvent molecules like water. However, they look different. From the viewpoint of the right here, on the negative potential, which is more negative than the point of zero charge, then it looks similar. However, as you go to the left here, on the positive potentials, which is more positive than the point of zero charge, they looks really different. So Grahame thought there is something happens which is related to the anions, because between those two curves the different thing is the anions, chloride minus ion and bromide anions. So the Grahame proposed the possibility of specific adsorption of anions. Let me think about the quantification of the adsorption. Here is the Markov effect parameter. Okay, adsorption would be function of concentration of the adsorbed species, of course. Also, point of zero charge would change with some adsorption. Therefore, point of zero charge is the function of the concentration of the specifically adsorbed species, especially anions. Here is the Markov coefficient beta. Beta is defined as 1 over RT. RT is a kind of energy term with the first derivative of something with respect to the ln log of concentration. Activity is a kind of concentration at the same excess charge of metal plate. What is the something? That is the PGC shift. I mean the potential shift of point of zero charge. So if no change in terms of point of zero charge, it means no adsorption. The point of zero charge is shifting to the more positive value, then it indicates cationic adsorption. Or if it is going to the more negative value, it means anionic adsorptions. Why negative shift for anion, positive shift for cation? Let me explain about that. For example, here is an anion adsorption. In that case, your the excess charge of solution side would be negative because you have anions. Then this negative excess charge of solution side would induce the positive excess charge of metal plate to compensate the excess charge of solution side. So right now we have plus sigma of metal plate. To keep the point of zero charge, or to obtain the point of zero charge, you should go to the excess charge of metal plate is going to 0. So to keep this value, you should apply more negative potential into the metal plate, because right now the sigma of metal plate is positive value. So negative potential shift is obtained for the anionic adsorptions. Here is the potentials of zero charge in various electrolytes. And sodium fluoride, and I have changed the concentration from 0.001 to 1.0. It means the anions, the concentration of anion is changing. However, in the cases of sodium fluoride, there are no significant change of point of zero charge. Minus 0.472, 472, 480, 482. It means no adsorption. Actually, the sodium fluoride is a well-known species having no adsorption on the surface of electrode. And let me change the anions or sometimes cations. Let's go to the sodium chloride. 0.1 molarity, 0.3 molarity, and 1.0 molarity. The point of zero charge is shifting to the more negative value with concentration. How about KBr? To the negative. How about Ki? Potassium iodide from minus 0.6 to minus 0.8 to the negative direction. So we could recognize that the anionic adsorptions for the case of chloride minus anion, bromide, or iodide anions. Then in our modern model, we have a specifically adsorbed species in the inner Helmholtz layer. We have one more things. Actually, in the previous models like Helmholtz, Gouy-Chapman, Stern, and Grahame models, we didn't have any solvent molecule layers inside of the inner Helmholtz layer. At 1963, Bockris-Devanathan and Muller have added the final layer onto the model for the electric double layer. That is the solvent layer. So finally, we have returned to the very first pictures of this chapter. We have two layers, Helmholtz and diffuse layer. In the Helmholtz layer, we have two different layers, two different sublayers. The first sublayers is the solvent molecule layers, sometimes having the specifically adsorbed anions. And in the second layer or sublayer of the Helmholtz layer, you could find the solvated cations if your electrode is negatively electrified. And then in the diffuser layer, you have distributions of solvated cations to compensate the rest of excess charge of the electrode. Then I have explained about that, and this Bockris-Devanathan and Muller model is the finalized modern model of electric double layer. That's it about the chapter 4 of electric double layer or non-Faradaic processes.